Hi everybody, this is Mrs. Ewald signing in, and I'm going to try in very few minutes here go over moles and molar mass. So, starting off, first thing, list as many counting group terms as you can. Example, a couple, when you hear somebody say a couple, right away what comes to mind is two. So spend just a few moments right now thinking about all these terms where right away a specific quantity comes to your mind. Go. Do 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 do. Okay, enough of that. You should have some idea. So, what's the purpose of these terms? So, a few of them, a few. Oftentimes, you're thinking of three or more. Couple meaning two. A lot of times, dozen. You hear the word dozen right away. You think of 12, or you think of baker's dozen. A baker's dozen would be 13. So there's different terms that we come up with, different groupings, and a number comes to mind. So the purpose of these terms is they right away provide to us a quantity. Okay, so it gives us a number. So special chemistry counting term that we use all the time, and we're going to use a lot more, is the mole. And I'm not talking about the little furry guys, although they're cute. And I'm not talking about the moles on your face. In chemistry, we are talking about the mole, which is a way to count large quantities of things. It is a constant. It's useful for conversions. We abbreviate it to MOL. We just lose the E, because it's so much shorter. But anyway, we just lose the E. And we also represent this when we get into our gas laws as an N. So that's the symbol that we use, the variable that we use for mole. As far as the quantity, this is what you need to know and memorize. And so when we talk about having a mole of something, it means we have 6.02 times 10 to the 23rd of it. That could be particles, molecules, whatever. And that's a really large number. So how big is that? When you have 1,000, that's 10 to the third, which is 1,000. And then you go to million, billion, trillion, quadrillion, quintillion, sextillion. The mole is huge, absolutely huge. And in fact, you can't really see it here. But look, it's 6.02 times 10 to the 23rd. That many zeros following. That is a very big number. Again, I say, that's really big. Or is it? So let's say, for example, I have a mole of something. What does that really look like? 1 mole of water is 18 grams, which is approximately 18 mils according to the density of water. And that's only about, that much. And I would have a mole of water molecules. Or I could have 1 mole of table salt, which is about 58.5 grams or a half a cup. And so this here would be about a mole of table salt. So when I look at those, they don't seem that big, but it's the molecules that make them up. How many do I have of them? So how do we get these numbers? How did I get this and how did I get this? That's what you should be asking yourself right now. They are from the molar masses. Molar masses? Well, where's that from? The molar mass is the mass of 1 mole of an element or a compound. So we look on the periodic table, your handy dandy periodic table, which you should always have one in your pocket or in your purse. So on the periodic table, you look and it would be the number on the bottom, which is underneath the symbol. And that tells you your units in grams per mole. This is very important. So it tells you the amount of grams per mole of that element. And one thing to mention is that when you look at this value, they give you a very large decimal because it's the averages of all of the isotopes, and so you have a decimal. And as far as we're concerned, in Mrs. Ewald's classes, you can go ahead and round to the whole number. It really does depend on your teacher, so please ask your teacher, whether it be Miss Heaton or whoever, what they would like. I know that in AP chemistry, Mr. Golubiowski would prefer that you write out the whole decimal when you're doing your calculations. I prefer just to use the whole number, except for chlorine, which we'll show as an example. But do make sure you ask your teacher always how it is you should round. And so here's examples then of molar mass examples. Here in this Erlenmeyer, you could see a mole of water. Again, it was that 18 grams. Here's a mole of carbon, a mole of aluminum, a mole of silicon, and then down here you're able to see other examples. So here's copper, here's lead, here's mercury. Just gives you the different amounts. This is sulfur. It appears much larger than the rest, but they're all 1 mole. So this gets into the application, which is determining molar mass. We're going to be using this later on when we do calculations with ideal gas law. So let's see. Here is what we would see on the periodic table. So this is the hydrogen, this is the oxygen. This here is the atomic mass, which is the number that appears underneath the symbol. So if I want to know what is the total molar mass of water, like we saw in the earlier example, how do I know that it's 18 grams? What I do is I look at this and I say, well, I have, according to my subscript, 2 hydrogens and 1 oxygen. Okay, now I look at my molar mass. So because I have 2 of them, I'm going to take 2 times my molar mass, and I'm going to round to the nearest whole number, which is 1 for hydrogen. And oxygen, I have 1 of them times, round that up to 16. So this is 2 and this is 16. You add it up for a total of 18 grams per mole. And that would be my molar mass that I would use in a calculation if I needed to. Here's an example with sodium chloride. So I have 1 sodium and I have 1 chlorine in this compound. So that would be 1 times my molar mass, which is 23. Notice how I'm rounding up. And then the chlorine is 1 times. Here I make this because it doesn't round up so nicely because it's so close to 35.45. It's so close to 35.5. So we use that to the tens place then. Multiply this out, that would be 23. For my chlorine, that would be 35.5. And then I would add it up. So this would be a total of 58.5 grams per mole. So I have just determined the molar mass of water and the molar mass of sodium chloride using my periodic table. I would like for you on your own to go ahead and try with these 2 examples and have these prepared for class. So sulfuric acid is H2SO4. You would do the same thing, total up each of your elements, multiply by the molar masses, and then sum them all up. And then here I'm providing the molar mass of sulfur, just so you have it handy. Same thing too for the iron 3 acetate. Only thing is, be very, very careful. Here I'll show you, you have 1 iron, but how many carbons do I have? I have the subscript outside, so it would not be just 2 carbon, but it would be 2 times 3, so I would have 6 carbon. And I would have 3 times 3, so I would have 9 hydrogen, and I would have 2 times 3, so it would be 6 oxygen. And then you would again multiply by your molar masses based on how many you have, take the sum, and get your answer. So try those 2 out for the next time we meet. And now let's go for an example of how we use those molar masses, because that's what's really important when we get into our calculating later. So we can use molar masses as a conversion factor. So as I said, the unit for molar mass is gram per mole. And again, we get those from the periodic table. But the way that you see this, I could write it like this, or I could write it like this, mole over gram. Beautiful, right? If you think about factor labeling and how we had those conversion factors, I believe we also called them conversion statements or statement equivalents. This is what we're going to use now. So here's an example. Let's say we have 3.04 moles of ammonia. We want to know what the mass is of that. This is when we get to first figure out the molar mass of ammonia. So in this molecule, so I have 1 nitrogen, I have 3 hydrogen, so 1, and I know the molar mass for nitrogen is 14, and I have 3 hydrogens, so it would be 3 times 1, which gives me 3, so my molar mass would be 17 grams per mole. I'm now going to use this as a conversion to go between mass and mole of ammonia. So I'm going to write out my given first, which is 3.04 moles of ammonia. I'm going to write that on the bottom in my denominator. Why? So that they cancel out, mole, and I want to get to grams, so I'm going to write that on top. And I know that 1 mole of ammonia is 17 grams based on my calculation above. Multiply across, and you end up with 51.68. But according to sig figs, I can only have 3, so this would be 51.7, and the answer would be in gram of ammonia. So I've just used molar mass by using the periodic table, figured out my conversion factor for ammonia to convert from mole into gram. Here's an example. Here's an example going in the reverse. So now I have gram and I want to get to mole. So I would set up 100 gram of ammonia. I would have gram of ammonia on the bottom. And now I'm still using that same conversion factor of 17 grams per mole from the previous problem. But I'm just reversing it. And I'm going to get 2 moles of ammonia. And again, I know 1 mole is 17 grams. Now I just divide. So this cancels. I leave with moles on top. So you divide that out, and it would be about 5.882 for sig figs, as in the beginning, moles of ammonia. Circle, and you are done. So I think that should take you through what you need to know, how to solve for the molar mass of any kind of compound or element, be able to use that as a conversion factor when going from moles to gram or gram to mole. And this will start you off. Also make sure that you know 6.02 times 10 to the 23rd is the Avogadro's number. And you need to know this because we're going to use those in conversions as well later on. Because we know then that 1 mole is that many number of particles. So good luck to you, have fun, and happy moles. Bye-bye.